Class C. Blue lights, music, everything.
A cafe.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for our show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Bernd Lienhard, who is the CEO of VORAGO Technologies, which is a fabless semiconductor company. Welcome to the show today.
Thank you, Scott. Thanks for having me.
So I know you spent many years at AMD, Freescale, Infineon, as well as companies like Siemens Semiconductors, to name a few. Can you tell us just real briefly about your work in semiconductor and how that has led you to VORAGO, and I believe VORAGO is formerly known as Silicon Space Technologies.
And we'll talk a little bit more about the company, what we're doing, but in a nutshell, we are providing radiation hardening solutions for aerospace and defense. And my first touch point, which actually made this opportunity so exciting, was actually my initial first 3 years as an engineer. So my first 3 years was really working as an engineer doing electronic work for the defense industry. And I can tell you, I think the most frustrating part for me was when, as an engineer, you have a task to do and you have a system to deliver. And the choices I had at that point in time, because it was defense, they were so limited. The components you could use, the selections you had, delivery times, service, what have you. So I was actually at a point where I was, after 2-3 years, extremely frustrated. And interesting enough, after almost like 25 years, it came back full circle, and now running a company which is actually trying to solve that issue for this industry. So it's pretty cool. Actually came in full circle here.
Well, I think that's a beautiful story, because some of the best innovation stems from our own personal frustration. And I think the area that you guys are working on is very fascinating. I mean, the fact that your product, HardSil, that's able to harden semiconductor circuits without having to redesign it, and then really allows for that hardness and reliability of semiconductors in very extreme conditions. So let's go back to the company. And aside from space, aerospace, and defense, are there other sectors that the company is focused on as well?
So the company being founded in 2004 actually had developed a technology platform. You said it's HardSil, Scott. And HardSil itself has actually 2 personalities. One goes really right into the middle of radiation hardening. The second one is actually a mechanism to allow semiconductors to still work and operate in extremely high temperature environments. And that's using standard off-the-shelf, standard CMOS technology, like you find, for example, in your smartphone, for example. And so the classical example for this, obviously, is oil and gas, where we've been having customers who are actually using our products in well management or in drilling equipment. So as I said, the technology has really both flavors and both personalities. You can use in either radiation hardening, or you can use it in high temperature applications. It's pretty amazing, actually.
Those are really interesting parameters. I mean, when we think about traditional fabless, semiconductor and the kind of foundry products that are out there, these are not the kind of typical requirements. It's more on the computational, the ability to do more edge AI analytics, those kind of things. This really affords a very interesting notion, because, certainly at Astor Perkins, we're very focused on very extreme use cases, and whether we're talking about space, defense, and survival. And tell me if you could share a little bit more on whether it's climate change or whether it's more the need for more resiliency, how is your product being more readily adopted than even before?
If you think about going back over the last, I would say the last probably about 5 to 10 years, and look what companies like SpaceX have done, Blue Origin and others have done, really getting to a point where space exploration and providing space-based system gets a lot more affordable, has actually fueled the need for a lot more computing power and a lot more electronics actually in space. And that has a couple of factors. As number one, obviously, we're replacing currently our existing Earth observation systems. We talk about climate change in a little bit. Second is intelligence gathering, threat prevention, and then obviously everybody talks about deep space exploration and obviously going to Lunar and going to Mars. So if you think about the idea is getting a lot more cost competitive systems to allow the deployment of electronics in space, whether it's in orbit or outside our orbit, has really fueled whatever we're doing over the last 2, 3, 4, 5 years, really.
And I think that's an excellent point because we're talking about not just potentially tens of thousands, but eventually hundreds of thousands of the smallest CubeSat and suborbital to larger satellites to space shuttles, crafts, rovers. I mean, just about everything that can possibly be out there, and they have to live out in those situations much longer, and of course be able to actually handle the computation, the storage, and the memory, and the AI as well on the edge. So puts a lot of pressure and a lot of strain. Can you talk about kind of your product portfolio a little bit briefly and how that is being navigated to meet the rising needs of in particularly space and defense?
Yeah, let's go back a little bit and take one step back before we really talk about our specific product. But think about everything which we currently design and use terrestrially or even in the air is basically commercial use and commercial design and commercial produced semiconductor-based electronics. And because of Earth atmosphere and the magnetic field, we are in a very fortunate situation that the laws to prevent any kind of radiation to do harm to this electronics. So it's totally fine to standard produce semiconductor components and put it into terrestrial systems. But by the time you expose the same kind of components in a radiation environment, which you see in low orbit or even higher orbits or even more, if you go into further out like Lunar or Mars or deep space, the more radiation exposure you have, and radiation does extremely harm to electronics and primarily to the components itself. That typically leads to either malfunction, loss of data, or complete destruction of it. So what's not possible is you can't use just standard design components and manufacture components and believe they're going to survive and be robust enough in that environment. So what we have done over the last 15 years plus, we have developed a technology platform and produced products on that platform which have the capability to survive that kind of environment, but still are based on the latest technology platforms. So basically using the same methodologies if you would use terrestrial, but harden them enough to survive an environment in low orbit space or anywhere else outside the Earth atmosphere.
I think you're spot on, and I think from our research, it's utilized in lots of different interesting ways, from upscreen cuts, redundant systems, exotic packaging, special design to expensive and specialized low volume processes like space that we're talking about. And because of the kind of duality of the radiation as well as the kind of this wide ranging temperature rise. So one thing you mentioned is ability to handle high temperature, but what about the other way? So in the case of, let's say, lunar or Mars or deep space, you have very wide low to high. How does it handle both spectrums?
So the lower temperature in most of the cases are not as critical for semiconductor as the higher temperatures. Think about the way I'm looking at a semiconductor has really two components. Number one is its functionality and its performance, obviously, which is spec'd. But every semiconductor, the way it's been manufactured, comes with what we call parasitics. So these are basically side effects in a semiconductor which are there, but you really don't want to have them. And the problem with these parasitics, they get extremely annoying to a point they can malfunction a part or destroy a part by the time you actually put physical stress on these components. And that could be either through temperature, and typically higher temperature are triggering more of these parasitics, or you go on the other side and obviously do radiation as well. So typically in the semiconductor space, the lower temperature are not as critical as the higher temperatures to be. So I think protecting a circuit or a component against higher temperature is typically a lot more difficult and requires a lot more different kind of approaches than typically for the lower temperature.
And to your point around some of these kind of side effects is, typically when a particular chip gets very hot, you have to cool it. So there's a whole cooling mechanism, and of course that also consumes a lot of electricity. In the edge cases that we're talking about, like in space, battery, low consumption, wattage are paramount. So can you talk about how your system is able to actually use less energy resources, including being able to kick off some of the cooling systems as well?
So by the time you're going to prevent this, what I said before, this parasitics really to become active, you just pretty much avoid any additional mechanical or thermal kind of additions to protect or heat or cool the part itself. So your total energy consumption of the system comes down because the component itself is capable of withstanding both the heat as well as a lower temperature side. You just avoid using that kind of additional capability at all because the component itself can survive it.
That's terrific. So basically less cost, less parts, and of course, less energy consumption as well.
Yes, and you always have to look at the total cost of ownership, I'm saying. So look at the power consumption of an entire satellite. If the components underneath it are able to sustain the temperature profiles on hot and cold, you can basically prevent them from having additional heating or cooling or even shielding in most of the cases, because obviously your radiation could be avoided in some cases with heavy shielding as well, which can be another element of cost and weight as well.
Let's just kind of briefly explore a little bit about the kind of use cases in space, in the sense that when we think about smaller like QSAPs that have a longevity of, let's say, 2 to 3 years before they're decommissioned, that's going to be very different from, let's say, more of a deeper space communication or satellite that needs to be out there potentially for a decade or more. What's the kind of spectrum and the kind of processes that's needed to support the different degree of hardening for radiation as well as high temperature?
When you say process, you're talking about semiconductor process or actually methodologies to do that? Because
semiconductor processes.
So for most of the hot spots out there, which currently been used to some degree in the low orbit area, typically the traditional technologies which are currently available, which are not expensive like FinFET, are totally applicable. What we've seen a lot more in the last 1 or 2 years, by the time we've seen missions where they've primarily used hot spots in the past, a lot of them has moved over a little bit more to the conservative side and complementing that hot spot with radiation parts, partially to protect very critical components of the mission, or operating specific watchdog systems to supervise the hot spots as well. And all of them, whether it's the radiation protected part or the hot spot, the technology can range from 180 nanometers down to 28 nanometers. So it's a relatively broad breadth, but we've seen that, as I said, as a development in this industry, that the industry has gone from COTS only now in the middle, and a little bit what I call a hybrid concept. Because even in mission lengths of 2 to 3 years, you have definitely impact and events which can definitely harm your entire system.
Absolutely.
So from that perspective, companies who believed, like in the past, they can run everything over 2-3 years with cost. It's just going through the learning curve and realizing, oh, an upgrade on their capabilities in terms of radiation hardening is actually good life insurance for the capability of the execution of the mission itself. And obviously, by the time you get further out and radiation becomes a lot more dominant, we have seen that the usage of more advanced semiconductor nodes gets less and less likely because it's a lot more expensive and it's a lot more difficult to harden smaller technology node against radiation because it requires completely different approaches other than our own currently. So think about everything in the LEO space is still mixed and can really range across the technology platforms. The further you move out, the less likely it is you're going to see something like a FinFET technology or lower technology platforms. They're more the exception than the norm.
I think that's a great point that you make. Can you provide a clarification or a definition of the LEO and GEO and how that relates to the future of space exploration?
So LEO definitely, as the name says, it's really a lower orbit, and the defining factor of that orbit is the exposure to radiation is existing, but it's not as strong, and because you still have the effect of the Earth's magnetic field, which is going to protect the electronics partially from some of the space-based radiation. The further you move out, Scott, the more you're going to get exposed. Obviously, that goes even up by the time you go lunar, you go Mars, to go interplanetary kind of exposure. So there is a increasing rate of potential harm by the time you leave the lower orbit. We've seen a lot more lower orbit deployment, as you said before, through constellations and small sats. A lot of them, either it's intelligence gathering, insurance-based systems, Earth observation, climate control, and you further go out, you add other elements like, for example, communication, other elements of that as well as defense-related activities.
I think we're kind of running out of time. There's a lot more questions I have, but when we think about terraforming, whether it's on the moon or Mars, or I think there's a research that recently came out around essentially a mega satellite that circumvents around one of Ceres moons, for instance. At some point, we're going to go beyond satellites to components that's actually going to be needed to support life and all the different ecosystems, whether that's a upgrade to ISS or new space station or the moon and Mars and so forth. What's the role of your company in all these different systems, and what are some of the areas that you wouldn't be able to actually support?
So that's actually an excellent question. So one of our prime benefits of our technology platform is the capability to deploy that technology in existing semiconductor nodes as well as into the most sophisticated one down to FinFET. So with that platform, you actually allow existing systems who are actually commercially used and non-radiation resistant to become radiation hardened and hence available for missions like this down the road. Where the classical approach is a lot more legwork because you have to specifically design a component for that environment, or you have to manufacture it in an environment which is very expensive and time consuming. So our technology sits right at a sweet spot where you can basically use existing designs who are designed for terrestrial applications with little to no effort and upgrade it to higher performing radiation resistant systems. So basically what you can do with that approach is you can replicate pretty much every application on Earth and make that available in an environment which is heavily exposed to radiation. So that basically allows you a fantastic bridge over to the next generation if it's used.
That's a huge benefit, and I think we can't even begin to explain this in the next couple of minutes in terms of the value of that and the speed and the cost. I mean, the fact that we're not having to create entire infrastructure or ecosystem. My last question for you is, because you're in a very, kind of a challenging, novel set of sectors and use cases, when you look back at your career as well as at VORAGO, any kind of lessons learned, product or project failure that you can share with others?
I think the biggest lesson learned is really underestimating a little bit on how a disruptive technology, even it's proven out, will take time to really find its way into new missions. I think this industry is still, because it's decades old with the same methodologies and way to do things, in mission success, because missions are so critical, because it also has human lives at stake, are extremely conservative when it comes to choice of technology and new technology, more disruptive technologies. So when I set off and saw the capability of that technology and the products we bring into the market, I really believed we can disrupt that market a lot faster than we actually do. And we're doing great, and we're growing pretty much doubling every year. But I would have said a couple of years ago that would have gone faster. But it's clearly, this industry is and remains extremely conservative. And I think companies like SpaceX have definitely paved the way to make this more commonly used. But for us, my learning was definitely, I would have thought we were going to be on a little bit of a different timeline here.
Well, very good, sagacious advice and insight as well. So with that, I've been joined by Bernd Lienhard, who is the CEO of VORAGO Technologies. Thank you for joining today.
Thank you, Scott. Thanks for having me.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.